Welcome to the session, everyone. My name is Corey Dow, and tech marketing engineer, and I'm joined by my colleague Arnaud Legao. And today we're going to be covering EVPN multi-homing phase 1. It is a very important feature to understand for the data center deployments. So that's why we're covering this in this TOI session. Okay, and so for the agenda, it's our typical agenda. I'll be covering the overview, use cases, and then I'll turn it over to Arnaud for the details and caveats. And then he'll hand it back to me for the rest of the session, including the demo at the end. Okay, so just this slide is just kind of historical for EVPN support on AOS-CX and kind of where we started and where we are now. So you can see we released, early 10.03 support, and then we've evolved this over time. And the focus of this presentation is the kind of the last two ribbons that you see on the lower left there. So support for layer 3 ECMP over VXLAN, which came in with 10.13.1000, and then support for EVPN multi-homing phase 1, which came in with 10.14.1010. That offered the initial phase of EVPN multi-homing interop, which was CX can now process route type 1s on the receive side. We can't transmit yet, so that's coming in a later phase, which we'll cover in more detail as we go through this. And then another important aspect to that is the layer 2 ECMP over VXLAN for single fabric deployments. This is also known as MAC aliasing, and we'll get into this in more detail as we go through the presentation. And so this doesn't completely cover all phases of EVPN multi-homing, but this is a really important first phase. And then we will cover the fully standard EVPN multi-homing, which will be both processing of route type 1, both on the RX and TX side, coming in a future release that is currently not yet committed. And we'll also support multi-fabric in that next generation of the feature set. Okay, so just as a reminder, just going to go through just what we've released already and what we support for CX. You can see the EVPN route types there. These are the ones that we've supported traditionally up until now. So there's route type 2, route type 3, and route type 5. And so you can see that we'll cover just each of these just briefly to show you what these are all about as a reminder. So for route type 2, this is for MAC and IP advertisements. And so these are used by a VTEP to advertise a MAC address, which has been locally learned, as you can see from the diagram. And in the case where you've got an ARP entry that is associated with that as well, that can be sent in a MAC IP route type 2 as well. So you can see that in the diagram where you've got a VTEP that's advertising host 1's MAC, and then host 2's MAC, and also the IP is sent in a route type 2 packet. Okay, moving on for route type 3. So this is the inclusive multicast Ethernet tag. So these RT3s are used for VTEPs to advertise the VNI, which is locally configured, allowing the automatic establishment of tunnels and the bump traffic forwarding between all VTEPs interested in that VNI. So as you can see, the edge VTEP on the left-hand side is, it's got L2 VNI 1 and 2, and then the two VTEPs on the right-hand side are interested in 1 and then 2. So these route type 3s are sent to advertise those VNIs out to the rest of the fabric. And then for route type 5, these are used to announce the IP prefixes, which allows the decoupling of the advertisement of an IP prefix from any specific MAC address. So in this case, these are just external subnets. So there's no MAC actually advertised for the remote subnets, but this is how the other VTEPs become aware of those external subnets, as you can see described here in the diagram. And as a final reminder, legacy behavior is to use the route type 2 for the MAC or MAC IP advertisement with the VNI field set to the VNI, which has been locally learned. But with symmetrical IRB, you can optimize the routed traffic to these remote hosts by using the L3 VNI can be sent instead of the L2 VNI using the host route redistribution feature. And continue on with some of these reminders, so that these will become important as we get into more detail in the presentation. So an EVPN instance is a base concept of an EVPN-based fabric. It's identified by its own route distinguisher. It has a unique MAC VRF table storing all the MAC addresses reachable through the attached VLAN or L2 VNI, and a MAC VRF has to be seen as a bridging table. And so AOS-CX supports two different implementations of this EVPN instance. So there's the VLAN-based service, and EVI in its related MAC VRF, it consists of only one broadcast domain or VLAN with only one bridging table. In this implementation, MAC VRF is identified by the route target, and the Ethernet tag has to be set to 0. And also the VLAN aware bundle service. It's an EVI and its related MAC VRF that can have multiple broadcast domains or VLANs, each of them having their own bridging table. And in this implementation, as you can see on the screen, the VLAN bridging table is identified by a combination of the route target and the Ethernet tag. And so other implementations, as you can see, do exist. So the VLAN bundle service, port-based VLAN aware service, but these are not supported by AOS-CX. And so the MAC VRF is only used for MAC addresses, and all route target setting IP information will be used by another table, the IP VRF table. So this terminology is related specifically to multi-homing support. So the first four are really kind of ones that we'll be talking about today that are implemented with the phase 1 approach, and then the last two will come into play as we move forward. So just kind of reading through these. So EVPN multi-homing, what does it do? It's the ability to connect an endpoint, so switch, server, firewall, to 2 or more different VTEPs which are not clustered. And so the concept with that is there's an Ethernet segment, which is a set of Ethernet links distributed across the different standalone VTEPs. And associated with that, there's an Ethernet segment identifier that's a part of that Ethernet route target that's sent out. So you've got route type 1, allows you to announce the Ethernet segment locally installed to the rest of the fabric, as well as the EVPN instance attached to these Ethernet segments. And so route type 4, we receive these, but we don't process these. These last two have to do with what will be our eventual phase 2 implementation, which has designated forward or election that currently we don't do anything with at this point. So again, so what's EVPN multi-homing? So multi-homing is a networking feature. It allows an endpoint to be attached to 2 or more different devices. So this provides link and device redundancy as well as efficient utilization through load balancing. That's what you can see here. We've got 2 multi-homing VTEPs, so VTEP 2 and VTEP 3. These are independent routers, but they have an Ethernet segment established down here with this lag interface connecting to host 1. So these are independent VTEPs, but they associate an Ethernet segment for multi-homing purposes. And so this is a standards-based approach or replacement for VSX multi-chassis lag, which is our AOS-6 implementation up until now. So this feature provides benefits. It's based on EVPN capabilities and the use of dedicated route types, and it removes the VSX architecture constraints. So no need for direct links between the peers, for example, the ISL, as well as platform constraints. So the same platform within a cluster. And so this capability, as you can see, is defined within RFC 7432 and RFC 8365. And as I just mentioned, so prior to 10.14, 1010, VSX multi-chassis lags remain the only mechanism for doing multi-homing on AOS-CX based devices. So continuing on, so before AOS-6 10.14 1010, so we didn't support multi-homing, which meant that any of the route type 1 or route type 4 packets were sent, they were received, but they weren't processed. And any route type 2 packet received from multi-homing VTEPs with a non-zero ESI, it was accepted in the BGP rib, but it was never programmed into the MAC table or the ASIC. So that meant traffic forwarding between AOS-CX devices and multi-homing was not possible, as you can see illustrated here in this diagram. And so with 10.14 1010, we've introduced the first phase of VPN multi-homing support, which consists of the interoperability. So now we're processing the route type 1 packets by AOS-CX devices, and the route type 2 with non-zero ESI can now be processed. And so now traffic forwarding between AOS-CX devices and multi-homing VTEPs is now possible. And as I mentioned, this will be completed through differing phases as we move forward. So for platform support, you can see that the feature is primarily targeted to the data center deployments, and this fills important EVPN competitive gaps. So we had a number of bids from customers that we weren't able to satisfy, and a lot of customers are waiting for this feature. That again, we delivered mostly in 10.14.1010 and 10.13.1000, so you can see the features and when they were released. So we have platform support for the 8325, the 9300, and the 10K, with some notations here just for the 8325. So the 8325P and H will be supported once those platforms are made available. They're under test currently. And then you can see some of the scale that's listed out here. So the number of overlay ECMP groups, we'll get into this in more detail. So basically 1022 is the number of ECMP groups that you can have on these platforms. And then the number of maximum paths for the EVPN address family is that these are all the same across these platforms. So for use cases, so multi-homing allows to support the following main use cases. So key one right off the bat is interoperability with different vendors that already are supporting EVPN multi-homing within the same fabric. So they're already sending the route type 1s and route type 4s, and we needed to be able to process those to be able to forward traffic correctly. So that's a key use case. And then also, as you mentioned, having the ability to support more than 2 devices to attach to external resources. So prior to 10.14.1010, this was only possible with VSX in basically 2 members. And then also just vendor agnostic. So we can attach to external resources to different types of VTEPs, either different vendors or switch families. And just one additional caveat, just that, so the only supported use case for 10.14.1010 is that the CX device needs to operate as either a leaf or fabric border. Okay, and with that, I'm going to turn over to Arnaud for details and caveats, and I'll be back in a little bit.
Yeah, thanks a lot, Corey. Okay, so let's move on with the different details and caveats. So you should see my screen now. So first, it's important to note that this TOI will not cover the different topics that you can see on that slide. So we will not cover everything related to split horizon filtering, designated forwarder election, and so forth. We will have an overview of the EVPN route type 4, redundancy mode, and Ethernet segment as well, but we will not go deep into these different topics. Why? Because those capabilities are related to the ability of a device to originate RT1 and RT4, which is not the case with this release or with phase 1. Okay, so as of 10.14.1010, so a CX device can act as a receiver of EVPN route type 1. So, okay, but what does it mean exactly? So it means that RT1 will be received and processed, which will allow the receiving VTEP to program the MAC addresses into its MAC table in case the RT2 that it receives has a non-zero ESN. And so doing that, it will automatically assign multiple ports for each MAC address. So this is what we are calling aliasing. And finally, it will also allow to remove the multi-homing VTEP as a next stop in case of a failure on this latest. This is what we are calling fast convergence. All those features will be covered in the later slides, but it must be clear that a CX device cannot originate RT1, so it cannot participate to an Ethernet segment. But in the meantime, even if it cannot originate RT1 and RT4, when it is used as a route reflector, it can reflect those routes if it receives them from multi-homing VTEPs. For the RT4 now, so a CX device will not be able to process them even if they can be received. Okay, so as I already mentioned, a CX device cannot participate to an Ethernet segment, so it doesn't need to process the RT4. But for troubleshooting purposes, those RT4 can be seen using the command show BGP L3 VPN EVPN, and we will see that in later slides. all that has been mentioned here is what is expected by the RFC 7432 in the section 8.6, which is named interoperability with single homing keys, which describe the interoperability between multi-homing VTEP and non-multi-homing VTEP. So in our case, the CX device being the single homing PE. We will see later on what is a single home PE and so forth. So in this output, let me just take my pointer. Okay, so in this output of the ShowBGP L3 VPN EVPN command, you can see new items or route types, which are colored in blue or in orange. So the blue lines that you can see here represent the route type 1 that have been received by a CX device, while the orange lines represent the RT4. Okay, so we will focus on RT1s in the coming slides, but as I mentioned, RT4 will have a quick overview on that, but we won't make a deep dive on this route type. Okay, so what are the concepts of Ethernet segments and Ethernet segment identifier? So let's start with the concept of Ethernet segment. So when an endpoint that we are calling a multi-homed endpoint is connected to 2 or more standard VTEPs, okay, that we are calling multi-homing VTEPs, with a set of Ethernet links, then this set of Ethernet links is called an Ethernet segment. But for many purposes, we need to give an identifier to that Ethernet segment. Okay, that's the role of the Ethernet segment identifier, or ESI. So that identifier, which must be a unique non-zero identifier, must be common to all VTEPs sharing the same Ethernet segment. And the fact that it must be unique is very important to prevent any issue on the traffic forward. So indeed, on the following diagram, if we configure the same ESI and the same EVI on a third VTEP that we can imagine here, okay, which do not have any connectivity to the endpoint, to the multi-homed endpoint, it will automatically participate in Ethernet segment operations like designated forwarder election or traffic forwarding, which could be very dangerous as it has no connectivity to the multi-homed endpoint. So if we come back now on the ESI, so the max ESI value, which is 10 times F, is something which is reserved and cannot be used to configure our own Ethernet segment. On the other hand, if the ESI is set to 0, it means that we are facing a single homed endpoint. And any other ESI can be used to identify an Ethernet segment. So if we just come back on ESI set to 0, so it's important to note that the term single homed is used in an EVPN context. Okay, so it only means that an endpoint or a VTEP is connected to a VTEP outside of an Ethernet segment. And in this case, no RT1 will be set. So this is a single homed endpoint. A single homed VTEP is a VTEP which is not originating RT1. Okay, so in our case, it could be a standalone VTEP or a V6 cluster. But as of today, as of 10.14, 10.10, AOS-CX is always considered as a single home VTEP. Okay, now let's discuss about the redundancy mode. So the redundancy mode is the way multi-homing VTEP will forward traffic to and from a given Ethernet segment, but also how they will manage redundancy in case of a multi-homing VTEP failure. So RFC 7432 defines 2 main modes. So the first one is the single active mode. And in this mode, only the first VTEP, which advertises a MAC address, will be used as a next stop by other VTEPs to reach out to that MAC address. Other VTEP are used as backup paths, as you can see on the slide, for that same MAC address and become active only when the primary VTEP has a failure. So the important thing to note here is that if there are multiple backup VTEPs, the traffic to the multi-homed endpoint will be clouded, as a remote VTEP will not be able to decide which one must be used, okay, in case of a failure on the primary VTEP. The second mode is called all active. So in that mode, all VTEPs hosting an internet segment will be used as next stops to a given MAC address. So the traffic coming from a remote VTEP and which has the MAC1 as an example as a destination will be load balanced across all multi-homing VTEPs using two mechanisms, BGP MACpass, and ECMP. So this way to load balance traffic is called aliasing, and we will discuss about that in the coming slides. Now it's important to note as well that AOS-CX 10.14, 10.10 only supports all active modes. So it means that any RT1 having the flag single active won't be processed. We'll cover that as well. Okay, let's dive into one of the most important pieces of EVPN multi-homing, so the RT1. So this new route type, which is also known as auto discovery routes, has two subtypes. So the RT1 AD per Ethernet segment and the RT1 AD per EVPN instance or per EVI. Okay. So each of them obviously has its own role. So that we will discover in the next coming slides. But globally, RT1 AD per ES and RT1 AD per EVI are used respectively for fast convergence and aliasing. It can also be used for some other capabilities, okay, like split horizon filtering and so forth, but we won't cover that today because we don't need it for phase one. It's also important not to forget that for any single owned endpoint, meaning not attached to any Ethernet segment, no RT1 will be originated by a multi-homing VTEP. Only the RT2 and RT5 are advertised with an ESI which is set to 0. So this behavior is the current behavior of AOS, even in 10.14, 10.10, and 10.15 as well. Okay, so first, let's begin with RT1 AD per Ethernet segment. So this route type is a mandatory one when EVPN multi-homing is implemented. So it is used by multi-homing VTEP to first announce their locally configured Ethernet segment to other VTEPs, as well as the redundancy mode. Okay, but on the other hand, it is also used for fast convergence when an Ethernet segment must be withdrawn. If we take a closer look at this route type, we can see the following items. So first, obviously, we have the Ethernet, so route type 1, the new NLRI, route type 1, Ethernet AD1. We have the route distinguisher, okay? And so this route distinguisher, depending on the vendor, can be manually set at the Ethernet segment level or auto-generated, okay? But the very important thing here is that it must be unique to each VTEP. This is not like in VSX, where in VSX you have the same RD for both devices. In that case, each multi-homing VTEP will have to get its own route distinguisher. So then we have the ESI, which is configured at the Ethernet segment level, and we also have the Ethernet tag ID, which is here set to 10 times F. Okay, so a route type 1 AD per Ethernet segment must have the Ethernet tag ID set to 10 times F. On the other side, the VNI must be set to 0 because there is no EVI associated to the Ethernet segment itself, so it has to be set to 0. And so the combination of all those values allow to determine that this is a RT1 AD per ES. If we want to see those routes in the BGP rib, we can use the command show BGP L3 VPN EVPN. And if you want, you can also add the argument route type 1 if you want to filter out. And as you can see here, we can see the layer 2 VNI, which is set to 0. We can have the Ethernet tag. We have the Ethernet tag, which is set to the max ET, so the max ET value, so the max Ethernet tag, so 10 times F. And we have the ESI as well. Okay, so now that we have seen how RT1 AD per ES is built, as well as how it will be processed by an AOS-CX device, there is another element which is very important, the root targets, which are used in this root type 1. So a root type 1 AD per ES is not generated until there is at least one EVI associated to the Ethernet segment we just created. Okay, this is because the RT1 AD per ES must use the root targets of the EVIs which has been associated to it. So the root targets which are defined at the layer 2, the L2 VNI level. So if there is no EVI associated, no root target can be used, and RT1 AD per ES cannot be set. On the other hand, if a new EVI is associated to the Ethernet segment afterwards, so let's say after 2 days, 1 week, 1 month, whatever, a new RT1 AD per ES will be sent with the new root target added to the list in the extended community. So just to illustrate that, we have 2 examples. So the first one, on this one, we can see here that in the extended community, we have configured 2 EVIs or 2 L2 VNI, which have their own root target. So EVI 101 and EVI 102. And so this RT1 AD per ES, which can be identified using the NLRI, is using the 2 root targets of 2 EVI which have been associated to the Ethernet segment. So that is when we configure a new Ethernet segment with new EVI. On the other side, when we add a new EVI to an existing Ethernet segment, let's say that we are adding an EVI 103, we can see now in the new RT1 AD per ES that we still have the 2 previous root targets, but we also have the new one, which is added to the list in the extended community. Okay, so we are now not sending a new RT1 AD per ES with a new EVI only or root target only. We are pushing the full list of the root targets of the EVIs which are associated to the Ethernet segment. If we take now a deeper look at those details in the CX CLI, so you can see that using that specific command, so show BGP L2 VPN EVPN, we can use to get the details on a route. We can use the RD of the sending VTEP with multiple information like the route type, the ESI, and the Ethernet type. Okay, so using this command, we can retrieve the information we mentioned in the previous slide. So once again, on this example, we have 2 times the same route because we are using 2 different route effectors in our network. So that's why we have 2 times the same RT1. Sorry, there are 2 entries that are coming from the same VTEP, but we have 2 route effectors. And so in the details, you can see the route targets which have been used. Okay, so we can retrieve the 2 root targets that we have seen in the previous example. So 101 coming from EVI 101 and EVI 102. And in case a new RT1 AD per ES is sent later on, because there is a new EVI, this field will be updated with the new root target. So in our case, with the root target from the EVI 103. Okay, so as we already mentioned, an important capability of EVPN root type 1 AD per ES is also the advertisement of the redundancy mode, which will have to be used. Okay, so remember the redundancy mode, single active, all active. In our case, we only support all active, but this redundancy mode has to be announced to the remote VTEPs. Okay, and so this is done thanks to the root type 1 AD per ES. So this specific capability is addressed in the RT1 as an extended capability. Okay, so we can see here in this capture that it relies on the ESI MPLS label to advertise the redundancy mode currently in use on the Ethernet segment. So here we can see the flag single active, okay, which is set to 0. And so when it is set to 0, it means that the redundancy mode currently in use is all active. In case it would have been set to 1, the single active mode would have been used. Okay, so now we have seen the RT1 AD per ES, and so we are now going to dig into the RT1 AD per EVI. So this route type is an optional one and used only when all active mode is configured, and because this mode requires what we are calling aliasing. Okay, so as I mentioned, it's only needed in all active mode because this mode requires that all VTEPs hosting the same Ethernet segment advertise their EVI attached to that same ES for load balancing purposes, even if some of them has no MAC addresses locally learned or dynamically learned on a given EVI. So if we now take a closer look at this EVPN route type, so first, obviously, we have the new NLRI, so Ethernet AD route type 1. And we also have the route distinguisher. So the route distinguisher is the one which is configured at the layer 2 VNI level. Okay, so we are not using a global route distinguisher like for the RT1 AD per ES. In the case of the RT1 AD per EVI, we are using the RD, which is configured at the layer 2 VNI level. The ESI is still the one which is configured at the Ethernet segment level. And the two differences, the other two differences are from the Ethernet tag ID. Okay, so in that case, it is set to 40, but this field should be set to 0 if VLAN-based service is in use, or to the Ethernet tag value if VLAN aware bundle is configured. And finally, we have the VNI, which must be set to the ID set at the layer 2 VNI level. Those values, or this kind of values, allow to determine that this is a RT1 AD per EVI. If we want to see those routes in the BGP RIB as well, we can use a command, still the same command, show BGP L3 VPN EVPN. And as you can see here, we can see the layer 2 VNI set to the VNI value that we had in the VNI field. The Ethernet tag set to 0 in that case, so it means that we are using VLAN-based service. And because we are using, sorry, I missed that point. And so the ESI as well, that has been configured and received in the ESI feed in the NLRI. The point which is highly important to note, it is that as of 10.14, 10.10, EVPN multi-homing only supports VLAN-based services. So it means that if any RT1 AD per EVI or RT2 is received with an Ethernet tag different than 0, then the route will be ignored. It will be displayed, but it will be ignored by the system. Okay, so if we want to get just a quick summary of the EVPN RT1, so here you have BGP table, and so the two first entries that we have in blue are the RT1 AD per ES. So we have one RT1 AD per ES, one per VTEP. Okay, so obviously if a VTEP has multiple Ethernet segments, we would have multiple RT1 AD per ES for a single VTEP, but this is not the case here. So here we have two entries, one per VTEP. On the other side, we also have the RT1 AD per EVI, so one per VTEP. In that case, we only have one EVI associated to the Ethernet segment. In case we would have multiple EVI, we would have multiple entries per remote VTEP, so per multi-homing VTEP. Okay, so now let's discuss about the aliasing capability. So one of the challenges we could have with all active mode is when a host and its MAC address is advertised by only one multi-homing VTEP as an example due to LACP hashing. Okay, so if we take this as an example, we have H1 with MAC1, so the traffic due to LACP hashing is only forwarded to VTEP2. So only VTEP2 will send a new RT2 advertising MAC1. Okay, so due to this situation, remote VTEP would only use the advertising VTEP even if the Ethernet segment and the EVI are available on other multi-homing VTEP having the same Ethernet segment. So this prevents load balancing when the remote VTEP send traffic to the host. Logically, when we have all active, we have to get all VTEPs capable to receive the traffic from remote VTEP and to send it back to Multihome endpoint. So in this case, this situation, it would be prevented. It would prevent load balancing between the different Multihome VTEP. So to fix this, EVPN multihoming embeds a mechanism which is called aliasing. And so this mechanism allows remote VTEPs to program all VTEPs, announcing their participation to an Ethernet segment and some EVIs as active next stop, even if some of them do not have the MAC address or the IP address installed locally. So that way, and as you can see on the diagram, VTEP1 will be able to load balance the traffic to host H1, even if VTEP3 did not advertise the MAC address. So there are two types of aliasing. So first, MAC aliasing, which is linked to MAC addresses, and so the MAC VRF table, and so thanks to the RT2 MAC only. Secondly, we have the IP aliasing, which is linked to the IP addresses, and so the IP VRF table, thanks to the RT5 and the RT2 MAC IP advertisement route. But as of 10.14, 10.10, it's important to note that IP aliasing is not supported. Okay, AOS-CX only supports MAC aliasing. Okay, so if we take a closer look at the backend and how it works. So first, we configure the Ethernet segment 10 on our two multihoming VTEPs. Then we configure and associate our EVI to that Ethernet segment. Okay, doing that, the RT1 AD will be sent to all RT1 AD per ES will be sent by all VTEPs having the ESI configured. So this RT1, in addition to the ESI, will include the type of redundancy mode currently used. On the other side, RT1 AD per EVI are also sent by all VTEPs, announcing the availability of the EVI, and so in that case, EVI 10.040. And so finally, a host which is attached to ESI 10 starts to send traffic through the VLAN 10.040. So LACP hashing between multihoming VTEPs and multihome endpoints sends the traffic to VTEP3, which automatically announces, like we can see here with the RT2, announces its new MAC address to remote VTEPs using a RT2, which includes the ESI. Edge VTEP1 that we have on the other side receives this new RT2 and program this new MAC address into its MAC table as the ESI matches the one received from RT1s. Keep in mind that the RT2 now have the ESI feed in the NLRI, which is set to the ESI configured as the Ethernet segment level. And so because both VTEP2 and VTEP3 announces the participation into ESI 10 and EVI 10.040, they are both programmed now as next stop, as you can see here, as next stop for this new MAC address, and traffic can now be load balanced between VTEP2 and VTEP3. On these outputs, we can see the two RT1 AD per EVI. Okay, so here and here. And then those RT1 AD per EVI are sent by the two multihoming VTEPs, and the RT2 as well, which is here, sent only by one of them. Okay, so remember, it was only sent by these three due to LACP hashing. If we now take a look at the MAC table, we can see the MAC address with two different remote ports, okay, which are the two multihoming VTEP. Okay, so we can retrieve this one and this one. So this IP address and this IP address are now set as active next stop for the same MAC address in the MAC table. And this is due to aliasing capability that I just explained before. But how it works in the backend? So in the backend, once the RT2 is received, based on information in the NLRI, it will create what we are calling a layer 2 destination group, which will have the list of all tunnels associated with DCSI as destination. So this group is linked to a MAC address, so it won't be created unless a new RT2 is received. Okay, so let's take a closer look at how it really works in the backend. So first, let's say your RT2 is received to advertise MAC M1, but we didn't receive the RT1s yet. So in that case, we create a layer 2 destination group, but with a single tunnel. So with a remote VTEP who advertised this MAC as a next stop to reach out to this MAC. Right after, we receive the RT1s from both VTEP1 and VTEP2. So once received, and because the layer 2 destination group cannot be updated, we delete the layer 2 destination group for MAC M1, and we recreate a new one, but this time with two tunnels having both VTEP1 and VTEP2 as next stops. Now, MAC M2 is advertised as well by both VTEP1 and VTEP2, and RT1s have already been received. So here, because the layer 2 destination group with both VTEPs as next stops already exists, we use it for MAC M2 as well. Then a new multi-homing VTEP, so let's call it VTEP3, sends RT1s for both Ethernet segment and EVI. So thanks to MAC aliasing, it has to be added to the list of next stops for both MAC M1 and MAC M2. So to do that, we delete the layer 2 destination group used for M1 and M2, and we recreate a new one with the three tunnels, so with VTEP1, VTEP2, and VTEP3 as next stops. Now, MAC M3 is advertised by two other multi-homing VTEPs, let's call them VTEP5 and VTEP6, having a different Ethernet segment and EVI. So we create a new layer 2 destination group with VTEP5 and VTEP6 as next stops of the two tunnels. Then a new multi-homing VTEP, let's call it VTEP4, is added to the Ethernet segment. So we now have a new list of next stops. So this list of next stops, being already used by another layer 2 destination group, we use it for MAC M1 and MAC M2. So we don't need to recreate a new layer 2 destination group, and M1 and M2 now use this existing layer 2 destination group. And finally, we receive a RT2 withdrawn for MAC M3. So it has to be removed from the MAC table. So the layer 2 destination group is not used by any other MAC, so we delete it as well. Okay, so for MAC aliasing to be effective, a remote VTEP must receive first an RT1 ID per ES, okay, and per VTEP to be aware of the Ethernet segment which has been created, as well as the redundancy mode currently in use. It also has to receive RT1 ID per EVI and per VTEP to be aware of the EVPN instance which are mapped associated to the Ethernet segment. And obviously, as you just explained, if there are no RT2, there is no destination group, and so there is no aliasing. So the third point is to receive an RT2 from at least one multi-homing VTEP advertising a MAC address. On the other hand, MAC aliasing could not be performed for several reasons. So first, because the flag single active is set into the RT1 AD per ES. Remember, aliasing is only tied to all active mode. In case of single active, there is a primary path and backup path, but there is no aliasing. So if the flag single active is received, we do not set aliasing. One important point on that, if let's say we have a set of three different multi-homing VTEP, if only one of them is sending RT1 AD per ES with the single active flag, while the two others send the RT1 AD per ES with all active, then the remote VTEP will set the access to the Ethernet segment as single active. Okay, and in this case, the two VTEPs which have the flag all active will be used as backup path, while the one which used single active will be set as primary path. Another point is when RT180 per AVI is received before the RT180 per ES, or aliasing will be put in place as soon as the RT180 per ES is received. Then also when the RT2 arrives before any RT1. So in that case, and so remember the previous slide, the MAC address would be installed in MAC table with only one next hop. But one next hop is not aliasing. Okay? So we need to get the RT1 to be able to install aliasing with multiple next hops for a sendback. And then obviously, if the ESI set in the RT2 doesn't match any ESI announced by the processed RT1. So, as we mentioned earlier, in all active mode, a MAC address could be learned and advertised by only one multi-homing VTEP. But in the meantime, aliasing will be able to load balance traffic with the MAC address as the destination as a destination across all multi-homing VTEPs. So the issue which could be faced is when another VTEP receives the traffic while it didn't learn the MAC address. In that case, it should drop incoming traffic. So how can we solve that? The solution comes from RT2. Keep in mind that that all multi-homing VTEPs remain independent VTEP, receiving all EVPN routes sent by all VTEPs in the fabric, including the VTEPs which have the same Ethernet segment. So in that case, if we look at the diagram, VTEP3, which doesn't have the MAC address dynamically learned, so locally learned, will receive the RT2 from VTEP2. It will check the SI included into the NLRI, and if it matches an Ethernet segment which is locally configured, it will program the MAC address in its own MAC table. And so in that case, the next stop for this MAC address will be the physical port associated with the Ethernet segment. And finally, as we already mentioned, so 10.14, 10.10 doesn't support EVPN multi-homing with VLAN bundle. Only VLAN-based service is supported. So it means that all RT180 per AVI or RT2 received with a non-zero Ethernet tag will be ignored and the MAC address will not be programmed into the MAC table. So if we look at this example, we can see here that we have two RT2 received with an Ethernet tag set to 40, and the MAC address are not set into the MAC table. On the other hand, with an Ethernet tag set to 0, MAC addresses are correctly programmed into the MAC table, even more with the two multi-homing VTEPs set as active next. Finally, one word regarding the host routes redistribution that we use with symmetric IRB. So as a reminder, host route redistribution allows to redistribute RT2 MAC IP using the layer 3 VNI, the route target, and the route distinguisher associated with the IP variable. So the main goal for that is to get each host as a /32 in the FIB routing. It will avoid to rely only on an IP prefix, which could be advertised by several VTEP. So the goal here is to get a direct link or direct next hop for a given host. It will avoid to send the traffic to that host to a VTEP which doesn't have the host locally known. So in that case, there is no change. Even if we are talking about RT2, it is a MAC IP RT2 with a VNI field set to layer 3 VNI. So it is automatically programmed into the FIB routing instead of the MAC table. Now let's move forward with EVPN fast convergence. So the issue we could get when a downlink port fails, as you can see here, is the massive amount of MAC addresses to withdraw. So the legacy behavior would be to send as many RT2s as MAC addresses locally learned. But the issue here is the time that it takes to send all the required RT2, but also the amount of time it could take for the remote VTEP to process all those RT2s. So this mechanism the legacy mechanism is highly time and resources consuming, and it could generate traffic drops because a remote VTEP could still be seen as a remote port while the downlink port is not operational. So to solve that, the solution is to rely on a mechanism which is called fast convergence or mass withdrawal. So this mechanism allows to efficiently and quickly signal to remote VTEP that they need to update their MAC table by removing the failing multi-homing VTEP as a next stop for all MAC addresses attached to a given Ethernet segment. To do that, once a failure occurs, the VTEP automatically sends a RT1 ID per ES to all VTEPs in the fabric. When they receive that information, the remote VTEPs will automatically update their MAC table, and traffic is moved to another multi-homing VTEP having the same Ethernet segment. Last point, in case there is no more VTEP for that given Ethernet segment, the MAC addresses are simply invalidated and removed from the MAC table. So let's dive into the requirements for fast convergence and what would be sent during this event. So first, when a physical link fails, the multi-homing VTEP using a BGP update will send the following route types. First, an RT1 AD per ES, obviously. Also, an RT1 AD per EVI, one for each EVI associated with the Ethernet segment. And obviously, one RT2 for each MAC to withdraw. So in that case, it is important to keep in mind that fast convergence does not replace the legacy behavior of EVPN. So it means that RT2s will be sent anyway and will act on previously received RT2s on the remote VTEP side. And so in that case, the RT1 AD per ES will first remove the multi-homing VTEP as a next stop for all MACs, all MAC addresses, and the RT2s will then withdraw the matching RT2s from the BGP route. Now, what happens when we only remove an EVI from an Ethernet segment? Okay, but the Ethernet segment is still up and running, and the physical ports attached to that Ethernet segment are also still up and running. So in that case, the BGP update will have one RT1 AD per EVI, so one per removed EVI, and the RT2s. And so here, because the RT1 AD per EVI is received without any RT1 AD per ES, it takes precedence over the RT2. Okay, so the RT1 AD per EVI will first remove the multi-homing VTEP as a next stop for all MAC addresses attached to that EVI or to VNI, and then the RT2 will then withdraw the matching RT2s from the BGP route. Finally, an important reminder, all other EVPN route types supported by CX, so the route type 3 and route type 5 are not supported by fast convergence. Okay, this in this case, each route, so RT3 and RT5, each route will have to be withdrawn one by one. So to illustrate that and the consequences that can be observed with fast convergence, so let's take the following example. So first, on the diagram that you have on the left-hand side of the slide, we have the link between H1 and L3 or L3, which failed. Okay, L3 is the only VTEP which has advertised the MAC address of H1 using RT2, as we can see here. So with a link failure, RT1 AD per ES is generated and sent, okay, by VTEP 3 or L3, requesting all remote VTEPs to update the MAC table. So if we look at the outputs that we have just here, we can see now that only one VTEP is still used as a remote port for H1. This is VTEP 2. Now, VTEP 3 also sends, as we have seen in the previous slide, VTEP 3 also sends RT2 to withdraw the RT2 sent to advertise the MAC address of host H1. So the RT2 is removed from the BGP rib, and because of that, VTEP 3 was the only VTEP which has sent the RT2 to advertise this MAC address. So it is also totally removed from the MAC table. So now that the RT2 withdrawal has been processed by the remote VTEP, we don't have the MAC in the MAC table anymore. So now this MAC address is no more reachable from remote VTEP. But thanks to the lag into LACP, host H1, which is here, now sends traffic through VTEP2. VTEP2 then dynamically learns the MAC address, advertise this MAC address using a new RT2, and the remote VTEP can now reach out to H1 because we now have a new RT2 and the MAC address is installed in the program into the MAC table. So this convergence can take between 100 milliseconds to 4 or 5 seconds. It really depends on the vendors and on additional mechanisms that we could use to optimize this convergence. On this slide, so as you will see in a withdrawn route, there is, and specifically in the NLRI, the VNI field is not present. Okay, we don't need the VNI field to withdraw a route or a set of routes. So as you can see here, we have two examples. So first is the RT1 ID per ES to withdraw an Ethernet segment. So we don't have the VNI field. And this is the same thing for this RT1 ID per AVI. So to withdraw an AVI, we don't have the VNI field. So as you have seen, so RT1 ID per ES are used in two different ways. So first, when an Ethernet segment is created, and then when fast convergence occurs due to a failure on a multi-homing VTEP. So how can we differentiate both use cases when we are looking at RT1? So first, when we advertise an Ethernet segment. So here you can see that the path attribute which is used is MP reach NLRI, and it uses the field NLRI. On the other hand, when it is used for fast convergence, the path attribute is set to MP unreach NLRI with a field withdrawn route. The only thing to note here also, in addition to what I've just mentioned, is the fact that you can find also RT4, because this RT4 will be used by the failing VTEP, multi-homing VTEP, to advertise the other multi-homing VTEP that it has a failure on the given Ethernet segment. Okay, so in this slide, we'll make a quick introduction to EVPN RT4, also called Ethernet segment route. So this EVPN route type is mandatory when EVPN multi-homing is implemented. Only when we originate RT1 and RT4, obviously, we do not need to process them as of 10.14, 10.10, but for phase 2, we should be able to manage and to process this RT4. So it is used for two main purposes. First, to discover all VTEPs with the same Ethernet segment. And secondly, it is used by VTEPs to elect the designated forwarder for a given Ethernet segment. So what is a designated forwarder? So in a set of multi-homing VTEPs having the same Ethernet segment, the designated forwarder is the VTEP which is in charge of bump traffic forwarding to the multi-homed endpoint. Only this device is allowed to forward bump traffic from the rest of the fabric to the multi-homed endpoint. All other VTEPs having the same Ethernet segment will drop this bump traffic. Finally, so one quick point, so something that we mentioned earlier in the presentation, it is a use of a CX device as a route effector. So a route effector does not install EVPN routes. It means that it doesn't originate the EVPN routes. It only reflects the routes that it receives. So it means that a CX device can be used as a route effector in an EVPN VXLAN fabric, which has multi-homing VTEPs, including RT1 to RT5. And because we do not install the routes, we can reflect routes which have a non-zero Ethernet tag, but also with the flag single active. Okay. And the final point for that is that as for any kind of route effector, the only useful command here is the show BGP L3 VPN EVPN, which will allow to see which RT1 and which RT4 are received and reflected. Okay, so that was for multi-homing. So now let's move forward with a complementary topic, which is layer 2 and layer 3 ECMP over VXLAN. So let's start with layer 2 ECMP over VXLAN. So before AOS-CX 10.14, 10.10, when several VTEPs sent the same RT2 advertising the same MAC address, only the first one was programmed into the MAC table. So this behavior was not compatible with the MAC aliasing capability that we just covered in the previous chapter. Now, with AOS-CX 10.14, 10.10, a new capability, which is called layer 2 ECMP over VXLAN, can be used to program multiple remote VTEPs as active ports for a given MAC address. So when a MAC address has several VTEPs as a remote ports, a MAC lookup will point to the different tunnel, as we have seen through the layer 2 destination. In that case, BGP ECMP is used to load balance the traffic across all available tunnels. So now, with layer 2 ECMP over VXLAN, MAC aliasing and the ability to load balance the traffic towards multiple multi-unit VTEPs can be achieved. Now, layer 3 ECMP over VXLAN. So before AOS-CX 10.13, 1000, because this is a capability which came with 10.13, when several VTEPs sent the same RT5 advertising the same IP prefix, only the first one was programmed into the routing table, into the field routing. Now, since AOS-CX 10.13, 1000, a new capability which is called layer 3 ECMP over VXLAN, we can program multiple remote VTEPs as active next hop for a given IP prefix. So when an IP prefix has several VTEPs as next hop, a layer 3 lookup will point to different tunnels. And so in that case, BGP ECMP is used to load balance the traffic across all available tunnels. Just to give you a bit of use cases, so obviously one of the first one is when you have a router which is connected to two different VTEP, tunnel VTEP, or multi-homing VTEP. And so in that case, the subnet behind this router will be advertised with two VTEPs. And so the two VTEPs will advertise those IP prefixes to the fabric. And so in that case, we will be able to load balance the traffic across all the VTEPs announcing the same IP prefix. One other use case which could be important is the interaction with NSXT, okay? Because with NSXT, you have the concept of edge routers, which allow to advertise the traffic within the overlay, the NSXT overlay, to the rest of the world, and so to the CX-based fabric. And so in that case, the edge routers could be connected to different VTEPs. Okay, and so the subnet into the NSXT overlay could be advertised by different VTEPs, and so we need to be able to load balance the traffic among the different edge routers. Final note on that, both IPv4 and IPv6 are supported. Now, just a quick example. So this first output allows to see that for same IP prefix, we received 3 different RT5. Okay, so advertised by 3 different logical VTEP IPs. The routes are doubled because we have 2 route effectors here. So with this second display, we can see what happens before AOS-CX 10.13, 1000. Only one route is put into the RIB, and so programmed into the routing table. So the selection of this route is based on BGP criteria, which could be the edge of the route or the router IP. And then in this new output, we have the same kind of result, but with AOS-CX 10.13, 1000. So you can see now that we have 3 different entries into the RIB, 1 per logical VTEP, and in the routing table, we retrieve those 3 different entries as well. In that case, layer 3 ECMP over VXLAN will be used to load balance the traffic towards the 3 different active next hop. So when using layer 2 or layer 3 ECMP over VXLAN, 2 criteria will be considered. First one, BGP max path, which allows to have up to 8 different remote VTEPs as a port for a given MAC or next hop for a given IP prefix. So the BGP max path is a number of hops that you allow for a given MAC or for a given IP prefix. But also the IP ECMP, okay, using the same machine algorithm that can be used for any other purposes. So it's important to note that configured algorithm will be the same between layer 2 and layer 3. Just to close, so let's see now different use cases of layer 3 ECMP over VXLAN with multi-homing VTEP. So the first one is when we have the following items. So an SVI configured on the two multi-homing VTEP as a distributed gateway, and an IP on host H1. So if we now look at the routing table on edge VTEP, we can observe the following things. Subnet S1 and SVI 10 both have two different active desktop because they are advertised by the two multi-homing VTEP. Okay, but on the other side, IP1, which is the endpoint, has only one desktop because it is advertised by only one multi-homing VTEP. And because we do not support IP aliasing, we do not take care about the ESI in the RT2 or RT5 used into the NLRI, so we don't automatically put VTEP3 as a potential desktop for IP1. Subnet S1, in that case, so S1 is announced by both VTEPs. Okay, so in that case, you can see that we have a router here. So routing with and routing is done using active mechanisms. So the subnet is announced by both multi-homing VTEPs. So we have the two VTEPs here, which are assigned to the subnet S1 on the edge VTEP side. And finally, if we are using active passive on the other end, active passive mechanism, so it means that S1 is only announced by one VTEP, so we will only have one VTEP as active desktop on the edge VTEP side as well. So to illustrate that, let's take the following example. So we display all routes from a given layer 3 VNI. So here, 11,000, sorry. So first we can see that we received different RT5 for two different IP prefixes. So each multi-homing VTEP advertising them. In that case, if we look into the routing table, we can see that layer 3 ECMP over VXLAN is considered. And so we now have each prefix with two different desktop. Then we have RT2 advertising a MAC address and an IP address, so, and only by one multi-homing VTEP, and it is using layer 3 VNI, so it means this is a host one. When looking at the routing table, we only have one entry, because even if the RT2 is advertised with a non-zero ESI, aliasing cannot be done because AOS-CX does not support IP aliasing. So only one entry is programmed into the routing table with only one next up. So the VTEP which advertises. The caveats now. So EVPN for EVPN multi-homing. So as we already mentioned, so only all active redundancy mode is supported. No single active mode. VLAN over bundle service is not supported as well. So the Ethernet tag must be set to 0. The IP aliasing is not supported for host, so the /32 host routes, and for IP prefixing. Support of route type 1 processing is only supported on devices used as leaves, and it includes when it is used as a fabric border. So the point here is to say that we do not support RT1 processing when on devices which are used as tunnel stitching points, such as multi-fabric borders. Multi-fabrics topologies are not supported, and as of 10.14.10.10, IPv6 underlay has not been validated. On the layer 2 ECMP over VXLAN side, so layer 2 ECMP over VXLAN with static VXLAN is not supported, as well as with MAC ACL with VXLAN. IPv6 underlay with layer 2 ECMP over VXLAN is not supported as well. We do not have separated load balancing scheme for underlay and overlay. So because IPSMP is a global configuration item, so we cannot differentiate between underlay and overlay. And finally, multi-fabric topologies are not supported, and VLAN over bundle are not supported as well. So that was for the details and caveats. So now for the configuration. So back to you, Corey. I let you take this part.
Okay, thank you, Renaud. Okay, so continuing on with the configuration. So it's not a lot to configure, as again, we only support the reception of the route type 1 frames. So as of AOS-CX 10.14.10, so we can only act as a receiver. There's no specific configuration required. We can use the maximum paths to indicate the number of remote VTEPs to get programmed for a given MAC or IP attached, and the default is 4. And once you change, if you change any of this configuration, then as you can see, all the BGP sessions will get restarted. And the only other knob that we have basically is the ECMP load sharing hashing algorithm, which can be configured in a space by default on the source and destination ports and the source and destination IPs. We don't typically see this altered in deployments. Okay, so just continuing on with some of the show commands that Arnaud has already kind of shown us. So it's just this is a way to filter just based on the route type 1 argument, just to look at specifically which route types you want to look at. And then we do have filtering capabilities, as you can see here as well, using route maps if that's required. And so getting additional details on an EVPN route. So this is getting a more granular view or more detailed view as to that particular entry, as you can see mentioned here. Okay, so this is also kind of a caveat. So you can see on the left, we have a little bit of a happy path, and then on the right, a little bit of a not so happy path. So this is just something to be aware of when you're configuring the maximum paths. So the happy path on the left, you can see that we're configuring it within the EVPN address family, and we're setting it to max paths 5. So that's within the supported range of 8 that we support for that address family. However, other address families can also support additional maximum paths, and you can see that on the right-hand side where we've configured max paths to 10. So that doesn't have the result that you'd think it does. So it sets the maximum paths within the global BGP configuration. That's not actually what you want, because underneath the hood, it's still only going to use 8 as the maximum path. So just something to be aware of as you're configuring this. And so just as the bullet mentions here, so the maximum paths configured at the address family level perspective takes precedence over the one configured at the BGP global level. Okay, and so this is just the max paths as part of the VSX context. So you can use a VSX sync to sync the BGP items, and so the maximum paths are part of that. You can sync that as well, as you can see illustrated here in the examples. And so we've also added a new capability to reflect the maximum number of ECMP groups. And so you can see the show capacities, L3 resources. This shows the maximum number of the tunnel groups, as you can see highlighted here, the 1022. So each ECMP group takes 1 entry, but if we're running dual stack, it'll use 2 different ECMP groups and take 2 entries. So just something to be aware of. And along with that show capacities command, we now have a show capacity status as well that can show you how many of those entries are actually in use. And you can see in this example, we have a number of different prefixes here on the top level of the diagram, but they all use the same next hop. So in that case, they're only using 1 ECMP group, as you can see illustrated here. And just continuing how to get some of the route type 1 stuff, you can pull this through the REST API. So here's an example where we're just doing a get of the BGP routes URI to get that information. And then MAC aliasing as well can be used using the MAC URI, as you can see illustrated here on the right-hand side. So this is a get. You can see that 1 MAC is advertised by 2 next hops, as you can see illustrated there, which is the same result that you get from the REST query. And in this example, is an example of a patch request. So what we're doing is just taking the maximum paths and we're altering it. We're changing it to 6, as you can see here. So you can use patch for that. You can use post and put to do that as well. And so best practices, probably best to leave the BGP maximum path as the default. So it provides load balancing up to the 4 different remote VTEPs as a default behavior, as we mentioned. This is suitable for most deployments, and generally only 2 next hops are needed for resiliency. So unless you have a need to alter this, you may just want to leave it as is. But if required, it can be increased to 8, as mentioned, and should be configured within the address family EVPN as opposed to the global configuration context. And as also mentioned already, just probably best to use the ECMP hashing algorithm as it is. But if you needed to disable any of these, this would be the way to do it with the CLI command. And for troubleshooting, it's all pretty much standard stuff. So you want to make sure that VXLAN's EVPN is up and running. So it's just checking the normal things, checking the BGP configuration, make sure your neighbors are established. check the EVPN configuration, make sure your tunnels are up, check the configuration of the VXLAN interface, make sure you have the correct VNIs, etc. And once done, so this is some of the specific troubleshooting related to multi-homing. So you want to check the configuration, but more specifically, you want to check the ESI and the route targets are configured consistently. And as we mentioned, only all active redundancy mode is supported. So make sure that's configured on all the VTEPs. For route type 1 auto discovery per ES, make sure those are received. And route type 1 with L2 VNI set to 0 must be received from the multi-homing VTEPs. And you want to check that there isn't any EVPN route type filtering implemented on the path that might prevent this from being received. Check that multi-homing VTEPs are not configured with VLAN aware bundle service because again, we're not supporting that. Ethernet tag must be set to 0 in EVPN routes receiving from the multi-homing VTEPs. And as we mentioned about the BGP max path, just make sure that they're set correctly as expected. Okay, and so for the demo, we've actually got a couple demonstrations that we're going to do here. So for the first one, it's really kind of covering a lot of the same show commands. This is the same environment that Arnaud used to do a lot of the screenshots. So we're going to just dive into this just a little bit more detail, but you can see where we're covering just the MAC aliasing as well as L3 ECMP over VXLAN. So you can see in this example here, we've got this prefix 10.110 is advertised by the two next hops, and then we've got MAC aliasing. You'll see that this MAC that's advertised over here, the 6F91, will be advertised by both VTEP and VTEP2 and VTEP3 in the table. So, and then we on the left-hand side, so single fabric, got VSX support here on the left-hand side, and we've got an active gateway configuration. So in the demo, pretty much what we're going to do is just do a ping, across the fabric to this destination here, and just look at the tables and then show what happens if we reboot one of these 5945s. And so don't usually include this in presentations, but we just thought it was important because not all of us are all that familiar maybe with the COMWAR configurations. So these are a lot of the display commands that you use not only just for multi-homing support, but how to dump tables and look at, are the tunnels established, look at the MAC tables, et cetera. So I'm just going to include this here for later reference. Yeah, so what I want to do is just kind of show what's required in the 5945 COMWAR configurations for the multi-homing support. So you can see in this example here at the top, so this configured this identically on the same. So we've on each of the VTEPs. So we got the global MAC configured there. And then for COMWAR, the multi-homing advertised ignore Ethernet tag, that's important. We need to have that in place to be able to process those route type 1 packets that are coming across. And I'm just going to kind of scroll through the configs just a little bit. And I just want to show the LACP configuration if I can get to it. Yeah, so you can see here, so we've got a bridge aggregation group 10 that's going down to a 3810 in the environment. So this is where we've configured the link aggregation, specifying the VLANs. 40 is the one that we're actually interested in for this demo. And then we configure the Ethernet segment index here. So you can see that this is configured with a 10, and that's set identically for both this 5945 as well as the peer 5945. And let's just kind of go through this a little bit more. So same configuration there on the second router, as you can see here, the BGP, well, not the BGP configuration, but the aggregation group configuration with the same ESI is configured there. And this is where we're configuring the LACP group. So again, these are independent routers, but they establish the same Ethernet segment going downstream. So they advertise the same LACP system MAC. And this is just the link aggregation summary. So we can see that that's all looking good. And this is just what I mentioned earlier about you need to have the ignore Ethernet tag set for COMWAR interoperability. And then we're just looking at the BGP configuration. So you can see we've got 34.13 on the top and 34.12 on the bottom. Same BGP AS, and it's just two different VTEPs. Okay, let's just kind of go through this to where it's a little bit more interesting. So the DF election, that's kind of what Arnaud already talked about. So like for any given segment, you're going to have one of the VTEPs is going to be primary or backup, which you can kind of see illustrated here. So this router itself is taking the backup role, whereas the other device will show primary. So not that important. Well, it's important for interoperability, but this is exactly the type of configuration or features that we need to have moving forward for phase 2 implementation. That's why I wanted to show that there. And this is something I ran into as well that I wasn't really understanding at the beginning. So like if you dump the MAC table, you see it's not showing any of the MAC entries that are learned from that bridge aggregation group. Well, there's one, but that's just kind of the switch MAC. So we're not learning the particular host MACs, and it's just the way Comware kind of implements this feature. So there's a couple other commands that you need to do to get a query of the actual MACs. The one that we're looking at is the 6F91 here. So you can see that it's pointing at the bridge aggregation group here. So this is displayed within the L3 VPN context, and then you can also do so within another context, the EVPN route MAC context, as you can see here, to look at that particular entry. So I've got that there. And then just kind of going through some of the commands just to show that the tunnels are up and established, and looking at the route tables. So we're looking at the 192.168.40.0 subnet. You can see that the next hop is the 35.5. That's the logical VTEP for the VSX pair. And same on both sides. And then just going through the same BGP L2 VPN command that we have screen dumps for. Same thing, you issue the same commands on the Comware devices as well. And then moving over to the 25 units, so we're just showing that we've got the tunnels established to both of the VTEPs, as you can see there. And then again, doing the show BGP L2 VPN commands. Not going to go into this because all of these screenshots are pretty much in the presentation. Just wanted you to be aware of what stuff to look at. Okay, and this is where we can see the MAC table here on the 8325. So this is a difference from what we saw with the Comware. So we've got a local configuration for the MAC table that we see that 6F91 MACs advertised by multiple VTEPs there, both the 34.12 and the 34.13. That's the same on both sides. And then for the demo, all we're doing is just taking the client that's configured to the 5945 and just doing a ping of the active gateway IP for VSX. And then what we're going to do is just actually reboot one of the 5945 routers, and you'll see you see how that got withdrawn. And so we don't see the .13 anymore, we see the .12. Yeah, and just the one last thing I wanted to show was once that router came back, you'll see that the external prefix here, as you can see here, we got 10.1.1.0 is advertised by both of the next hops as well as an external resource. Okay, so that's pretty much for this demo. So let me go ahead and close this down. Okay, and so for this one, it's really just demonstrating the MAC aliasing like we just saw previously, but also the programming of the maximum paths. So in this particular demo, what you'll see is it's virtualized through Ixia. So we've got virtualized VTEPs, as you can see here, VTEP 2 through VTEP 6. And actually the top should have said VTEP 7 because that's a VTEP as well. But what we're showing in the demo is basically, the next hop in the programming. So as you'll see, there's 4 that are programmed by default for the maximum paths, and that's what we see in the table. So even though there's 5 next hops for that particular prefix, we only see 4 in the table as a result. And so with the demonstration, we'll change that, and you'll be able to see what that looks like. Okay, so this is Ixia, basically just using the EVPN support in Ixia to virtualize those VTAP routers. So you can see the BGP configuration for each of them, the OSPF configuration, just to show that the underlay is up. And so then we're going to start up the virtual routers. And I'll kind of speed this up a little bit. We just start those stacks, and then we kind of come through here. And you'll see that we've got them established. Just disregard the other two, 1111 and 1112 aren't active in the topology. And so for that 511110, you can see it's advertised by all of the remote VTEPs, as you can see there. Okay, and then the same thing here. So that particular MAC, it's advertised by the 4 different VTEPs. Again, because we have max paths set to the default of 4. And this is just starting up the traffic for the demo as well. So let's skip on through that. So you can see we're receiving traffic across the environment. And you can see the ARP entry there as well, advertised by the 4 different next tops. And this is where we're changing the maximum paths to 2. So we configured this within the global context, but this really should have been configured within the address family, just probably as a best practice. And you can see now the table has changed, so we've only got the 2 next tops there instead of the 4 that we had prior to that. And so that's pretty much it for this demo that I wanted to show. And for additional resources, I've provided the link for RFC 7432. This details the EVPN multi-homing feature from a standards-based perspective. And with that, we've reached the end of the presentation, and I'd like to thank you for your time.